Okay, welcome to this introduction to model fitting with MATLAB. This is going to be pretty introductory, so I'm not going to assume any familiarity with model fitting at all, although I will assume some familiarity with MATLAB. Basically, model fitting is an important skill because it helps you to identify underlying trends in your data. And that's useful because once you know what those trends are, you can start using them to make predictions. So model fitting is all about finding a mathematical function that will capture or represent the underlying trends in your data. So usually you have to start with some kind of an informed decision about what that underlying trend might look like. So you might choose a linear function, a straight line. Sometimes you'll be modeling things that follow an exponential growth pattern like this. For more complicated relationships in your data, you might need to use a polynomial, like a second order polynomial, or higher order polynomials like third or fourth or even fifth order. So you can see the higher order polynomial functions are more sophisticated, and therefore they can capture more sophisticated relationships in your data. But let's just jump right in and start with an example first off. So from your MATLAB command window, if we go load census, that's going to load up some example census data. I think it's from the US, but it doesn't really matter. So this, in your workspace, you'll now see a vector called CDate. That's the date that the census was taken. And this other vector called pop is the population at the time of that census. So let's just plot this data and just take a look at what it looks like here. And we'll throw in some axes labels because that's what you're supposed to do, right? Okay, so let's take a look. All right, so over the years, starting in the late 1700s up to almost 2000, the population seems to follow this nice growth pattern, which looks pretty exponential, right? I'm told that economists often use exponential models to represent population growth. So this seems like a good candidate for an exponential sort of trend line or model to be fit. So why don't we go ahead and try fitting an exponential model to that. Now MATLAB makes this easy with the fit function. I'll show you how this works. So we use the fit function, we give it the sort of the x data, the predictor variables, and the y data, or the predicted variables. And then we tell the third argument is the fit type. This is where we tell it what kind of function we want to fit to the data. So if we want to fit exponential model to this data, then the command is exp1, or the argument is exp1. And then if we run that, MATLAB's going to fit an exponential model to our population data, and it spits out these statistics that we'll come back to in just a second. Let's, just for fun, try, in addition to the exponential model, let's try a second order polynomial. Oops. Now this second output argument is a goodness of fit object. And that contains some statistics about how well the model fits the data we've given it. So we'll use poly2 to fit a second order polynomial. And then just for kicks, let's also do a sixth order polynomial and see how that works. Okay, so we fit these three different models now, an exponential model, second order polynomial, and sixth order polynomials. We can use the MATLAB plot function to see what these fit models look like now compared to the original data. So we'll plot the exponential model first. Turn the hold on so we can see all three models on the same plot. Plot the second order polynomial model. We'll make that one blue. And plot the sixth order polynomial model. Let's make that one magenta. Okay. Let's put a legend on here to make it intelligible. Almost there. Okay, let's take a look now. Okay, so here's the three models that we've fit to our data. Let's make this bigger. So the blue line, the red line is the exponential model, the blue line is the second order polynomial, and the red line is the sixth order, the pink line is the sixth order polynomial. So we've just fit these three different models to our population and census data. Now the question is, which one is the best? Which one should we actually use? So to answer that question, there's a few things we can look at. First, we can look at the statistics that we kind of breezed over at the beginning. So let's start with the statistics that MATLAB sort of spat out here for our exponential model. So you can see here's the actual exponential function that MATLAB has fit to our data, and it has these two parameters in it, the a and the b parameters. And so these a and b numbers here, these are the a and b coefficients that cause the best fit for that exponential model with our data. So here's the value of the a parameter it calculated, and here's the b parameter, and these are the confidence intervals. Okay, so if you look at these confidence intervals, there's a bit of a red flag here because this one, the confidence interval includes 0, right? Which basically means that we can't say with statistical significance that the a parameter is actually different than 0. So that is a bit of a warning sign. But if we look at one more thing I want you to take a look at here is the R-square statistic in this goodness of fit object. So the R-square is a number between 0 and 1. It's just a measurement of how well the model, how well its predictions actually correlate with the data that we gave it. So 1 is the best, and this model has an R-square coefficient of 0.98, which is very good. Now let's compare that with the second-order polynomial model. So it has these three coefficients. None of these confidence intervals include 0, so that's good. And its R-square is 0.999, which is even better than the exponential model. So it's a better fit to the data by this metric than the exponential model was. Now let's take a look at the sixth-order polynomial. It has, a number of different coefficients. Again, none of the confidence intervals include 0, I don't think. Nope, okay, so that's good. And this one has an even better R-square statistic of 0.999. It's essentially a perfect fit. So by the R-square metric, it looks like our sixth-order polynomial is probably the best fit for the data that we have. Now the next thing we want to do is plot what are called the residuals. So the residuals are basically the errors between that best fit line that we saw and the actual data points themselves. So let's just plot all of these on this same chart here. We can use the MATLAB plot function again. To plot residuals, all we do is give it the model, the data, and this residuals argument, and that tells it to plot the residuals. Do the same thing for the second-order polynomial, 2, and the sixth-order polynomial. Okay, and they should all be on the same plot here. Good. So what this is then, if we take those best fit lines that we saw before and kind of stretch them out so they're flat and horizontal, and then look at how the actual data points deviate from those lines, that's basically what this chart is. So the top one here is for the exponential model. See, the red line represents the best fit model, or the best fit line through the data, and you can see how the data points are distributed around that best fit line. So the difference between the data point and the line itself is called a residual. It's basically just the error between the best fit line and the data point. So what we're looking for, or I guess the red flag that you're looking for, is that if the residuals sort of follow some sort of a systematic pattern, if the error is systematic in some way, then that's a bad sign. It means that the model hasn't fit the data very well. So you can see that with the exponential model, the residuals start off small, and then they're below 0 for the first half, and then they kind of come up to be above 0 for the second half. So there's kind of this pattern to the way that the residuals fall. And that's an indication that this model hasn't fit the data very well. Also, the residuals are quite large, right, in terms of the actual number. Then if we look down here at the second and sixth order polynomial residual graphs, these residuals now, they're not as systematic as the exponential, which is good. They're also smaller than they were for the exponential model, which means that they're a better fit than the exponential model was. The sixth order polynomial seems to have the smallest residuals overall, but both the second and sixth order polynomials seem to be pretty good fits to the data. So at this point, I think we can kind of rule out the exponential model as being a good model for this population data. The R-square wasn't as good as the other two, and the residuals seem to be kind of systematic. So it seems like the exponential model is not going to fit our data as well as we might want. Now there's one more thing we can look at to help us decide between, I guess now we're just deciding between the second and sixth order polynomials, and that's to look at these models' predictions. So let's close everything. start over here. Let's plot now the original data, and then over top of that we're going to plot the second and sixth order polynomial models' predictions or their forecasts into the future. And maybe that'll help us decide which model is kind of more reasonable. So, actually, I guess the way we do this is we just set the limits of the x-axis to extend into the future. Let's go up to 2050, the year 2050, and then we plot our model. We'll make the polynomial, second order polynomial blue again, and now we give it this pred_obs argument. That tells the plot function to plot the model's predictions along with their confidence intervals, which will be interesting for us. Okay, so let's take a look at each model's predictions. Okay, so we could add a legend to this, but I think we'll figure it out. So the blue line is the second order polynomial, and the pink is the sixth order polynomial. And we can see now how their predictions extend into the future. And this is interesting, right? Because the second order polynomial predicts that population will continue to grow in the way that we kind of expect it to. And it has nice, pretty tight confidence intervals around its predictions. On the other hand, the sixth order polynomial, it totally diverges, right? It fits the data really well in the range for which we have data, but then as you extend into the future, its predictions just become unintelligible, really. Like its confidence interval is actually predicting that population could be negative, which doesn't even make sense. So what has actually happened here is that the sixth order polynomial has overfit the data. We fit it too well to the point where now we're not modeling the underlying trends in the data anymore. Now we're modeling the little idiosyncrasies about the data. And as a result, this model, its predictions are no longer valid when you get outside the data range. So, by this, by everything we've seen so far, it looks like the second order polynomial is probably a pretty good model for this population data. And out of the three options we looked at, that's probably the one that you would go for. In general, this overfitting effect is something that you need to watch out for. It can cause a lot of problems, and it can happen anytime you try fitting a complex function to data that has a fairly simple underlying trend. And that's what we did here. We took a sixth order polynomial and tried to use it to describe data that really its underlying trend is only a second order polynomial. So the extra complexity in the model worked against us by overfitting the data. Overfitting can also happen if you try to fit a model to a data set that's simply too small. By that I mean that you have too few observations or too few rows in your data table. In any case, though, the best safeguard against overfitting is to have a completely separate set of data that you use to validate your model. So you fit your model on one set of data and then you test it on the other set, and if your model is good, it should have similar performance on both sets. Okay, so now you know how to fit models of various types. You can look at their R-squared and their coefficients. You can plot the residuals, and you can see their forecasts. So why don't you go ahead and give this a try. Let's load up, or first you have to download, I guess, and then load this U.S. immigration from 1950 to 2006. I'll show you what's in there. There's a vector of years where U.S. immigration data was recorded, and a second vector called immigration that shows how many people entered the United States in those years. So try loading up this data, see if you can fit an exponential model and a sixth order polynomial model to this data. Plot your fitted models and see if you can see which one you think is better, or if neither of them seem very good, see if you can see why that is. So yeah, go ahead and give that a try. Pause the movie, come back, and we'll compare what we think. Okay, so let's take a look at this U.S. immigration data and see how well we can model it. So first, let's just plot it, just so we can see what it looks like. Right, so same thing, we've got years on the x-axis, immigration on the y-axis. We can see it generally follows kind of that same exponential looking trend, with the obvious exception of this 1 year. I think what happened there was that there was some new law passed that made it easier to immigrate in that year, and so there was some kind of huge influx of immigrants. Anyway, what we'll do is let's try fitting our exponential and polynomial models. So fit immigration exponential model first. try that again so we can see the statistics. There we go. Okay. Now let's go ahead and plot these models. The exponential model. And the polynomial model in blue. Okay. All right. So just at first glance here, let's move this legend out of the way. Right, so at first glance, we can already see that neither of these models is really doing a great job, right? So the exponential model, it follows the right general curve, sort of, but it's not actually passing through this collection of data points, though, that we want. Right, it's overestimating the immigration in every single year except for this one bizarre year. The polynomial, the sixth order polynomial is just going crazy. It's a sophisticated model, so it's trying to use its wiggliness to capture as many data points as it can, and as a result, it's just all over the place. So neither of these models is really working very well, and it's what it comes down to is that it's because of this outlier point right here. So sometimes in your data you get one point or a couple points that are, they just don't make sense. They're just different, and as a result you don't, it doesn't actually help to include them in the model fitting process. They're not helping you understand the underlying trends in the data. They're just skewing things and making it hard for your model fitting to capture those trends. So I'm going to show you a simple way to remove outliers. What we'll do, actually, I guess I was going to plot the residuals, but you already know how to do that, and we don't need to do it. So yeah, let's go ahead and we'll skip ahead to the removal of the outlier. Now there's a fine line between removing outliers and cherry picking data, right? Like you don't want to remove outliers just for the sake of getting a better model fit. That's not really fair. So the best way to go about removing outliers is to decide before you even see the data, before you even try the model fitting, decide on a good outlier removal strategy that you'll use. One common outlier removal strategy is to remove any points that fall more than 1.5 standard deviations away from the fitted line. That's a fairly, unbiased, fair way of removing outliers that you can use to get rid of those pesky points that don't really help your modeling. So let's just go to the screen here. Here's kind of the code you can use to do that outlier removal strategy. The feval function is going to evaluate our model, our exponential model, at all of the year points. It's going to use our model to make a prediction for each year in that year vector. Now this is going to identify the points that fall outside that 1.5 standard deviations. You can go back and take a more thoughtful look at this code later to see how it's working if you like. Now we use this exclude data function to actually mark or generate a list of indices of points that we want to consider outliers. Okay, so if we look at that outliers thing we just generated, 0.9 is flagged with a 1, so that it's flagged as true, meaning that 0.9 is an outlier point based on this criteria of being 1.5 standard deviations away from our exponential line. So now that we've done that, let's refit the models. We'll refit our exponential model. Year immigration. We're still using an exponential model, but now we give it this additional exclude argument, and we pass in the outliers vector that we just created. So now the fit function is going to do the exponential model fitting, but it's going to exclude that outlier point. So it's not going to include that outlier point in its model fitting process. Let's do the same thing for our polynomial. Poly 6. Okay. All right, let's plot these now. See if this looks any better. Plot. All right. Okay, so it looks a lot better, right? The red line is the exponential, and it passes through kind of the center of these points in a growing exponential sort of pattern, which is what we would expect. The sixth order polynomial now is not as crazy, right? It actually hits most of these data points and passes very closely to the ones that it doesn't hit exactly. So our models are fitting a lot better now. Let's check their residuals. So we'll try the exponential model's residuals. And, oops, and the polynomial model's residuals. Okay. Okay, so both of these residual plots look really good. Like, obviously there's the outlier point, that's way out there, but that's because we ignored it in the model fitting. The rest of the points are all, fairly close to the line. There's no real observable pattern to how they differ from the line, which is great. So both these models seem to be a fairly good fit to the data. And let's confirm that by looking at, oh, I cleared it. Let's confirm that by looking at the fit statistics. Right, so an R squared, for the exponential model, an R squared of 0.97, although this A coefficient still includes 0 in its confidence interval. That's a great R squared coefficient, though. And the polynomial model, R squared of 0.998, which is very high. However, this model now, we've got the P1 coefficient, P2, P3, P4, P5. Actually, every single coefficient has 0 included in its confidence interval now, which is a big red flag. Right, so that means that this model has fit the data like perfectly because of it's a sophisticated sixth order polynomial. But we can't say with statistical significance that any of the coefficients it's calculated are actually meaningful or are actually different than 0. So that's an issue. So just based on that, we might want to pick the exponential model. It doesn't fit as well, but we could more kind of conservatively trust it. Let's go ahead and plot the forecasts too, just to see what those look like. Okay, so we'll plot the original data. And then we will plot our forecasts. First, we'll set the limits to extend into the future the way we want. So let's plot immigration between 1950 and we'll forecast up to 2013. Right, because we only have data up to 2006 at this point. So we'll pretend that we're a 2006 version of us forecasting immigration into 2013. Oops, so we'll give it the Fred-Obbs argument. So far we're probably going with the exponential model. We're less worried about it having overfit the data. And its R squared is good. It seems to fit reasonably well. We're just going to check the predictions into the future and see how reasonable they look. Okay. So the exponential model, which is in red here, it shows kind of this growing exponential trend to the immigration. The polynomial model, which is in blue, you can see that because this last year in our data set was sort of uncharacteristically high, that has caused the polynomial model to sort of zero in on that, and now it's predicting immigration to sort of skyrocket over the next few years. So that's an indication that maybe our polynomial model has overfit the data again, right? So it's captured all these points, but as a result, it's kind of making these wild guesses about what's going to happen outside the range of data we've given it. So again, it looks like the exponential model here is probably the best, of the two we've considered, it's probably the best choice. Now I just want to real quickly do a little experiment. Let's load up this function you'll have to download, or this mat file you'll have to download. It's called US Immigration 1950 to 2013. So we'll just load up that. Now this actually includes the real immigration data up to 2013. So let's plot our exponential model again. And now let's plot the real data. To see what really happened. Okay. Right, so all these blue dots along the exponential curve line are the ones that we had at the time we fit the model. But then look what happens to the immigration after that. It starts to, the trend actually reverses and it starts sort of dropping back down. Now that probably has something to do with the financial collapse in 2008. But the whole reason that I decided to show this is just to illustrate that even the best, most carefully fit model is still just a model, and its predictions can fail, right? So it's just important as we do our modeling process, and as we get bogged down by R-squared statistics and confidence intervals and forecasts and stuff, to just remember and have kind of a sense of humility and remember that it is still just a model, and its predictions are not, they're not prophecies. They're just, just statistical extrapolations. So it's important that we understand sort of the fallibility of modeling and predicting. And if someone else is going to be using the model that we come up with, it's important that they understand it too. So we have to be able to communicate it clearly. That predictions are just predictions. Okay, great. So, let's go ahead and, well, first I'll point out that all the stuff we just did on that immigration is in the curvefitting.m file that you can download and take a look at later and work through if you'd like. Oops. Okay, so this curve fitting stuff that we've done so far is great if we have a single predictor variable and a single predicted variable. But for a lot of stuff you're doing, you might have multiple predictor variables all trying to predict a single, or that you want to use, sort of together to predict a predicted variable. So for example, I don't know, maybe you're trying to model some behavior as a function of multiple neuronal signals or something like that. So in that case, one option that you could use would be multiple linear regression. So as an example, let's load up car small, which is a sample data set. It has a bunch of, I don't know, measurements, I guess, from various cars. Right. I guess there's not much to say about that. So let's go ahead and let's try to fit, just as an example, I'll show you how this works. We'll fit a multiple linear regression model. The command is fitlm for linear model. Let's say we want to be able to take the number of cylinders a car has and its weight, and we want to be able to predict from that how many miles per gallon it's going to get. Okay, so we'll do the linear model for that. Now MATLAB spits out, here's the linear function that it fit. X1 is, in this case, is the number of cylinders, X2 is the weight. And then these are the, and then there's a sort of an intercept term here as well. So the intercept and the X1 and X2 coefficients that have been calculated are all here, along with their p-values. Instead of confidence intervals, now it gives us p-values that show whether these coefficients are statistically significant, and they all are, right? P-values are all very small. We have the R-squared statistic, which is 0.76. Now, R-squareds are all relative, right? Before with the curve fitting, we were getting really high R-squareds of 0.999 or whatever. For this problem, we're getting an R-squared of 0.76. Like some things are just harder to predict than others, right? So whether an R-squared statistic is good or bad is going to be kind of relative to the problem. So let's look at the residuals. There is, for linear models, there's a plot residuals function, and we just give it the model that we created. Now, the way we looked at residuals before was by looking at the best fit line and how the residuals kind of fell around the line. This is telling us the same information, but just in the form of a histogram. All right, so we can see that the residuals are kind of normally distributed around 0, which is exactly what we want, except for these two, which are way out here. So that indicates these two are probably outlier points. If we wanted, we could go back and remove those the same way we did before. That would probably give us a little bit better model. Now, once we have this model, we can also use it to make predictions. So let's predict miles per gallon and a confidence interval of miles per gallon using the predict function for a car that has 4 cylinders and weighs, let's say, 2,000 pounds. Right, so using our linear model, we can predict that if we could build a car with 4 cylinders that weighed 2,000 pounds, we could probably expect 31 miles per gallon, with a confidence interval that ranges from 30 to 33-ish. Right, so that's, using linear regression in this way is very simple. All the same principles, I guess, apply about overfitting and stuff, although it's pretty hard because linear models are so simple. It's pretty hard to overfit a data using a linear model, so that's not as much of a concern, but all the same principles do apply. So linear regression, fairly straightforward. Why don't you give it a try? Load up the Challenger O-ring data, download it and load it. Now in this Challenger O-ring data, you have 2 sort of matrices. There's this temp PSI. So this shows the first column is the temperature, and the second column is a leak chest PSI that were recorded at, 23 different space shuttle launches. Okay, and then this distressed rings vector shows how many of the shuttle's O-rings were thermally distressed during that launch. So I don't know a lot about space shuttles, but I guess the rockets have multiple sections, and when the rocket is blasting off, it heats up and the sections start to expand, and there's gaps between them, and so you have to seal those gaps with some sort of an O-ring to keep the burning fuel from shooting out the sides of the rocket. Now on the Challenger space shuttle, which was launched in, I think, 1986. That space shuttle was launched at an extremely low, or an unusually low temperature, and one of those O-rings failed, and the shuttle exploded just a couple minutes after launch. So anyway, just take a look at this data and see if you can create a linear model to predict the number of distressed rings based on the temperature and the pressure. Let's go ahead and pause the video and we'll come back in a minute. Okay, so let's take a crack at this O-ring data. So we'll go ahead and fit our linear model, fit LM, use the temperature and PSI as predictor variables. And we want to predict the number of distressed rings, that's our predicted variable. Oh, whoops. There we go, got to spell it right. Okay, so this model seems to work. The R squared is 0.4. Again, that only really is meaningful if you were comparing this to some other model, because different problems have different degrees of predictability. So let's use this linear model before we do anything else to predict how many O-rings will be distressed if the temperature is 53 degrees, which is what it was on the day that the Challenger space shuttle was launched. So we'll get the number of distressed rings and the confidence interval. We use this predict function. So this Challenger space shuttle was launched at a temperature of 53, and the PSI was 200, I am told. Okay, so our model predicts that 1 ring will be distressed in those conditions, with a confidence ranging from 0.6 rings to 1.6 rings, which is kind of awkward, and we'll talk about that in a minute. But first, if we just go back to, well, first of all, I guess this tells us that one of the rings will be distressed, which is probably a good reason not to launch the space shuttle in those conditions. But if we go back and look at these coefficients, the second coefficient, which is the coefficient for the PSI, is actually not statistically significant, at least not by any conventional standards. Right? Its p-value is 0.27. So let's remove that one and try modeling it again. So let's just extract, we'll just call it temp. Let's extract the temperature data. I'm just calling it temp because I don't actually know how to spell temperature at the moment. Okay, so there's the temperature data, and let's refit the model now. With just the temperature as the, oh, I guess I didn't know how to spell temperature. Just the temperature as the predicted the predictor variable, and distressed rings as the predicted variable. Okay, so now our model is simpler, which is good, by the way. Simple if you can get away with a simpler model that performs just as well, that's always better. And the both coefficients are statistically significant now. Our R squared has dropped a little bit, but you know, it's still in the same ballpark, I believe. Yeah, it's 0.37 instead of 0.41, so very similar. Let's plot it now. We can plot our model. Now it shows us, you know, these x's are the data points that we fed it. And the red line is the linear model, what it predicts, how many, or the number of predicted distressed O-rings, and the dotted lines are the confidence bounds. Right, so that's easy. I should, by the way, I should be adding labels, X and Y labels to these plots as I create them, but I think you can figure that out. Okay, so all this stuff on linear regression is in the multiple linear regression.m file, along with some other suggested future reading. So you can check that out if you're interested. Okay, so we mentioned, or we pointed out, I guess, that you know, it's kind of weird to say that you know, 1.6 O-rings are going to be distressed, or 0.6 O-rings. That doesn't really, you know, it doesn't really make sense, right? What we really want to know is, are there going to be O-rings distressed at all, or what is the probability that this launch will jeopardize some O-rings in the space shuttle? So now we don't want to predict a continuous quantity anymore like we have been doing. Now we want to predict a probability. So a logistic regression model will tell you that. It'll tell you the probability of something based on a number of predictor variables. So fitting a logistic regression model fits the logistic function, which looks like this, to your data. Right, so this function kind of, you know, it takes a continuous input and squashes it to be in the range of 0 to 1. Which means it's good at representing probabilities, which are always in the range of 0 to 1. So let's take a look at how this works. Just as an example, I guess, let's say that we're doing some kind of behavioral experiment where our rat has to choose between option A and option B. And let's say that we're varying some test parameter to see how that affects the rat's choice. So we want to measure the probability of choosing A, say, as a function of that test parameter. So let's just generate some random hypothetical data for that experiment. So our test parameter, let's see, generate some normally distributed data. So this, I'm just generating this completely, you know, randomly. It's not really meaningful the way that I'm generating this data. I'm choosing it purely because it will make a good illustration. All right, so let's just view this random data. Now we could plot the choice data versus the test parameter. I'm just adding a little bit of jitter here to make it easier to see. That's all this next part is. Okay, so I will add some labels to this. Okay, test parameter on the x-axis, and the rat's choice is on the y-axis. Okay, so right, so we see the value of the test parameters down here. So each of these dots would represent like one trial, I guess, in the experiment. And the x-axis shows what the test parameter was in that trial, and the y-axis shows whether the rat chose, you know, option B or option A, or maybe it's A and B, doesn't matter. Okay, so now what we want to do is fit the logistic function to this, and that will then, we can use that logistic function output to represent the probability of the rat choosing choice A as a function of the test parameter. So the command now is fit GLM, which stands for fit generalized linear model. So our test parameter is the predictor variable, the choice is the predicted, and now this these next arguments are basically, it's telling MATLAB to use the logistic function. There are other options that work better for different distributions of data. For most things, logistic regression works just great. Okay, so we fit logistic regression model. Now let's make some predictions using it with their confidence intervals. Again, we use the same predict function as we've been using for the linear model. Let's make predictions in the range of 5 to 15. Okay, and then let's just plot that stuff and see what it looks like. Should have actually left this on, then we can plot on top of it. So we'll plot the predictions and now the confidence intervals. Okay. Right, so now you can see, so the blue is the original data. I guess we could, that's good. We'll just chop it off at about 8. So it's easier to see. Okay. Right, so the blue dots are the trial data, right? And this red line now shows, based on that trial data, what is the predicted probability of the rat choosing choice A here as a function of our test parameter. Right, so you can see as the test parameter increases, our probability of choosing A goes from 0 and slowly climbs up to a probability of 1 where he's going to choose A every time. So now this model basically can let us predict the probability that the rat will choose one or the other. So the logistic regression is useful anytime you want to predict an event happening or a probability of something based on continuous predictor variables. And this can work with multiple predictor variables too. So let's, just as an example, let's add some random data to our test parameter vector to simulate 9 more predictor variables. So we're going to take our test parameter vector, and now we're going to add some completely random data to it. We're simulating 9 more predictor variables here now. But because we're generating this data completely randomly, it's not going to have any bearing, it's not going to have any relationship with the rat's choice, right? So what we're doing here is simulating 9 more predictor variables that aren't actually meaningful in this experiment. And this is actually quite a common situation where you might have a lot of data collected, a lot of different variables were measured, and you don't actually know which ones are important and which ones aren't. Now, MATLAB doesn't know which ones are important either, right? So if we just go ahead and refit the model using all 10 variables, it just goes ahead and crunches through the numbers and spits out the the fit values for all 10 variables. But if we look at the p-values, here's the new ones we added. None of these ones are statistically significant, right? And we expected that because we generated them randomly. We know they're not important. So one approach in this kind of situation where you have a lot of data and you want to just pick out the parts that actually matter for your model is to use a stepwise model fitting technique. So how that works is that you select the single best predictor variable to fit your model with, and then you try adding each of the other variables in turn to see if they improve the model, right? And then you add a third one, etc., until you keep doing that until adding more variables no longer improves the model. So MATLAB has a nice function that will do this for you. It's called stepwise GLM. So that's going to fit our generalized linear model now in a stepwise form. There's also, I think, a stepwise version of the linear model fitting too, so you can use a stepwise approach when you're doing multiple linear regression as well, which could be very handy. So we want to do stepwise logistic regression using those 10 test parameters to predict the probability of choice A. Now there's a whole bunch of additional, arguments now. So just bear with me for a second. And then the distribution again. Okay. So now these extra parameters are telling it to start with just a constant term, so just the simplest possible model. And as an upper limit to the model complexity, we're going to consider each of the terms individually. You also have the option, if you say interactions or something, like that. It will consider interactions between predictor variables too. We're not gonna do that here. So this is going to be no interactions included. The criterion it's going to use to decide if a model is better or worse is the R-squared. And then the binomial distribution again is the same as before. Okay, so now see it added the first test parameter, which is what we expected because we know that that's the one that actually matters. And then it quit because adding a second term didn't actually improve the model at all in terms of its R-squared. So here's the final model now. It's automatically kicked out those 9 irrelevant features for us. The coefficient it does have is statistically significant, and the R-squared is 0.49. Great. So, and like I said, you can do stepwise linear regression as well. Okay, so why don't you give this a try? Load the Fisher Iris dataset. So in this dataset, there is a matrix of measurements taken from 150 different flowers. I'm not totally sure, I'm not a botanist, I'm not totally sure what on a flower you measure, but apparently there's at least 4 things you can measure about flowers. And then the species vector shows what species the flower was from. So there's Setosa, versicolor, and virginica. 3 species of flowers, 4 measurements from each flower. So try to make a logistic regression model to predict whether a flower belongs to the virginica species based on those 4 measurements. And see if all the coefficients for the model are significant, and if they're not, try to fit a second model using the stepwise method. Thanks. Okay, we're almost done here. Okay, so we want to predict whether a flower belongs to the virginica species based on these 4 measurements that are taken from the flower. So first let's create a new vector, because the species vector has a bunch of strings in it, and we're really only interested in whether something is virginica or not. So let's create a new vector called y that will tell us if the flower is virginica. Right, okay, good. And then we can fit our logistic regression model, fit GLM, the measurements as predictors, and this y as a predicted variable, binomial distribution. Let's do that again without the semicolon. Okay. Okay, good. So here's the 4 coefficient. Well, there's an intercept and 4 coefficients for the 4 measurements that we take from our flowers. Great. So we can see though that, are these, okay, so these 2 are not statistically significant, right? So it looks like we probably could get away with a simpler model that just has 2 terms in it. So let's try doing this in the stepwise way. Stepwise GLM, using the measurements, y. Okay, now there's like a million arguments again, right? Criteria. R-squared. There's other criteria you can use as well. Some are probably better for different situations. You probably could consult a statistician to get all the options. Oh, what did I do wrong? Distribution. There we go. Oh, yeah, okay, so it actually looks like we can get away with just one term. Right, so we have now this simple logistic regression model. It added just that single term, the 4th measurement, whatever that is, and it got an R-squared of 0.85, and then it couldn't improve on that by adding any extra terms. So that's great. So we can get a good model just with a single term. It's a simple model. That's excellent. Now we can take a look at how this model works using this plot slice function. This is a handy function for visually looking at logistic regression models, or generalized linear regression models in general. So we just say plot slice, and we give it our model. Okay, so now on the x-axis is the value of our measurement, and the y-axis shows the probability that this flower belongs to the virginica species. So the green line is sort of the predicted probability, and the red dotted lines are the confidence interval. So now we can just enter, what if this measurement is 1? Well then, it's got basically a 0% of belonging, 0% chance of belonging to Virginica. If the measurement is 2, it's basically a 99% chance. Yeah, so that's how this works. You can use this plot slice function with multiple predictor variables too, and it gives you kind of a nice interactive way of seeing the effect of each variable. Okay, so all this is in the logisticregression.m file that you can download and take a look at. And there's some suggested further reading in there as well. Okay, so that's it for this video. So at this point, you can fit a variety of curves to data using data that has a single predictor and a single predicted variable. You can check goodness of fit by considering R-squared statistics, coefficient p-values, and residuals. You can kind of do a basic check for overfitting by looking at the model's forecasts and just looking at the fit. You can do multiple linear regression and logistic regression, and you can do the stepwise versions of those methods. So that's an excellent start. Now I'm no statistician by any means, but you can always email me if you have any questions or comments, and I'll do my best. Okay, thanks very much.